Now that we have a formula which tells us how to compute the length of a curve on a given interval, we want to actually practice using this formula, see how it works, how we might actually integrate some of these functions, and we want to think a little bit maybe about how this works with our intuition about what length actually is. So example number 3 is asking us to compute the arc length of the function r of t equals 5t to the 3 halves minus 1 on the interval from 1 to 4. We want to compare this to the arc length of the function s of t equal to 5t to the 3 halves plus 4 on the same interval. And we want to think about why it compares the way it does. We'll see what that means after we've computed the arc lengths of these two functions. So let's start with the arc length of r of t. So in order to do this, we need r prime of t. So r prime of t is equal to, in this case, we use the power rule, 15t to the 1/2 over 2. Cool. So we have r prime of t. We want to compute now the integral from, let's see, we're on the interval from 1 to 4 here, of the square root of 1 plus r prime of t squared dt. So it's important to note that since we are using a new variable here, since r is a function of t, this is r prime of t squared, this is a dt. So keep that kind of sanity check in mind. If you find yourself using dx here when you have some t's on the inside of your integrand, that's a bit of an issue. So let's see. So we're integrating from 1 to 4. We want to substitute in square root of 1 plus, let's see, so r prime of t, we said, was 15t to the 1/2 over 2. Simplifying a bit, we have the square root of 1 plus, well, let's see, 15 squared is 225. T to the 1/2 squared is just t, and 2 squared is 4. So with this setup, we notice that this looks a little bit tricky, except we have a nice linear function inside the square root here. So if we use the u substitution, u equal to 1 plus 225t out of 4, then we're going to get that this integral here, so we get du equals 225 out of 4 dt, which is to say that 4 du out of 225 equals dt. And now we're integrating from t equals 1 to t equals 4 of the square root of u. Du, or dt rather, is 4 du out of 225. So we get 4 out of 225 times the integral of u du is u to the 3 halves times 2/3. We're evaluating from t equals 1 to t equals 4. So that's going to leave us with, let's see, 4 out of 225, or 4 times 2 is 8 rather. 225 times 3 is going to be 675. U, we said, was 1 plus 225 out of 4t to the 3 halves, evaluated from 1 to 4. And now we can actually go ahead and compute. So 8 out of 675. Let's see. 1 plus 225 times 4 over 4 is going to be just 225, which is a nice round 226 to the 3 halves, minus the thing evaluated at 1, so that's going to be 229 out of 4 to the 3 halves. Lovely. We have some kind of number here, and that is going to represent the length of whatever this curve is. Cool. So we finished the arc length of r of t, so maybe we also want to think about the arc length of s of t. Notice here that s prime of t is the same as r prime of t. S of t, if you remember, is 5t to the 3/2, so s prime of t is also going to be 15t to the 1/2 over 2. And so when we're doing this integral here, we're doing the same integral from 1 to 4 of square root of 1 plus s prime of t squared, so that 15t to the 1/2 over 2 squared dt. And since this is the same integral, we get out the exact same number, this 8 out of 675 times 226 to the 3/2 minus 229 out of 4 also to the 3/2. So maybe we want to think about why these two integrals are, or why the two arc lengths are the same here. And in order to do that, I'm going to need another page. So now that we have this, we can think about the fact, maybe about the relationship between r of t and s of t. So r of t we had was equal to 5t to the 3/2. What was this one? Minus 1, and the other one was plus 4. S of t is 5t to the 3/2 plus 4. So if we think about their graphs on the or on any interval, but specifically the interval that we care about from 1 to 4, so maybe let's make r of t blue and s of t green. R of t is going to look something like this, and s of t is going to be a vertical translate of that shifted up 5 units. So it's going to look something like this. Since these curves are vertical translates of each other, maybe let's write that down. Vertical translates. It certainly makes sense that they should have the same length. And that's exactly what our arc length formula tells us based on the previous computation, that when we take vertical translates, we're going to get the same length. So length is preserved under translating some curve up or down. You can check on your own a little bit if you'd like, that length is also preserved under horizontal translation. So I encourage you to maybe think about that on your own. All right, I think that's going to be it for this video, and the next one we'll take a look at another example.